Hello AP Physics students. It is Mr. Kennedy again. Happy Monday. We're going to be talking today about Ampere's Law Part 2. We talked about Ampere's Law a little bit last time, and today we're going to be finishing up some ideas in Ampere's Law, and some of it's going to seem really familiar to some things you did a while ago with Gauss's Law. Also, keep an eye out for an email that I'm going to be sending to you. The College Board is going to let you take your AP exam at home, it looks like. Kind of like an at-home test. Apparently they have some kind of security features they're going to put in, and the exam will not cover all of the units that are normally in AP Physics. But, in my personal feeling, I'm going to keep teaching you magnetism and electromagnetic induction. Why? Because whatever course you're planning on taking next, you should need to know those topics. This is supposed to be a course in college level physics. Every college level physics would have magnetism and electromagnetic induction in it. I'm not so worried about what's on the AP test, but when you're preparing, you won't have to prepare for everything, except you won't have to prepare for those last couple units. But I think this is material you should know. This is vastly important stuff. So I'm going to keep covering it as if this is a normal course. As if we're actually normally in school. So let's jump into it. And the first thing we're going to do, again, is going to seem familiar to some things we did before with Gauss's law. And let's say we have a wire. And here's our wire right here with a radius r. And that wire is going to have current coming out at us. So there's current coming out toward us. And the question I'm going to ask here is, first, what's the magnetic field on the inside and outside? And then what's the direction of the magnetic field on the inside and outside? I'm going to actually reverse those couple things and go with the direction first. But we're going to examine what happens on the outside and then on the inside. So again, this is very similar to Gauss's law, where we took a charge, and when we look back at, for instance, insulating charges, and then we examine what the electric field was on the inside and outside. Now we're going to look for what the magnetic field for the wire is on the inside and the outside. So first, the direction. When we look at the direction of the magnetic field, I take my right hand, and I point my thumb up, curl my hand around. So on the outside, the magnetic field will look like this. It'll be that circular pattern. On the inside, well, when I'm on the inside, I still have current coming out from all the different regions. So the only part that affects me is the part inside of wherever I am. So when I point my thumb, I will still get a magnetic field in a circular pattern. Same circular pattern, just on the inside. We're going to see this is not going to be the same magnetic field as this one. They're going to be a little bit different. But let's look at what happens when we choose our Amperian path and then put it all together. So if we look at Ampere's law, the first thing, the integral of B dot ds equals mu naught times the current enclosed. And we're going to do the outside first. So for the outside, what I do is I choose a path that matches the magnetic field. That path is a circle. So I'm going to choose a path here that matches the magnetic field. It's a circle. And there I have it. So if that's the case, B on this whole path is going to be constant. So that's just B, it comes out. I have the integral of ds. And mu naught times the current enclosed. Well, how much current did I enclose? I enclosed all of the current here. So I'll just have I. So B, the integral of ds equals mu naught I. Well, the integral of ds going all the way around, I'm at some radius r, because remember, little r is where you are, and it's b 2 pi r equals mu naught I. So b equals mu naught I over 2 pi r. In other words, for us, the outside of the wire, it doesn't matter what's happening on the inside. The outside of the wire just behaves as if the whole current is there because the whole current is there. Very similar that we saw with Gauss's law when you were on the outside of an insulating charge. It didn't matter what was happening on the inside. Now when we go on the inside, we're going to do another Amperian path. and I'm going to make it line up with the magnetic field, so it goes right along the same direction as the magnetic field. There it is. Now for this Ampere path again, we'll still do Ampere's law. The integral of B dot ds equals mu naught I enclosed. Well, on that path, the magnetic field will just be constant, and then I'll have 2 pi r. But the problem is now I don't have all of I. I'm not enclosing all of the current. I'm only enclosing the part that's inside here, inside that path. The stuff outside doesn't matter. Again, very similar to Gauss's law. So what I do is I use a ratio of the areas, because for that current, it's pi little r squared over pi big R squared. So make that squared a little bit better. So this is not the whole current. This is this little r, which again is where you are. That amount divided by the whole amount is the fraction of the current. So I'm not getting all of it, I'm getting just part of it. Now I'm going to cancel some things out here. And when I cancel some things out, what I'm going to be left with is that the magnetic field will be mu naught I little r over 2 pi big R squared. Now, this should be familiar again. As a matter of fact, on the AP test, it's so familiar that they have to do some questions with graphs to make sure you understand what's going on. But notice that what's happening here is on the inside of the wire, as I go further and further out, I get more and more magnetic field because this is proportional to R. So at 0 radius, I have no magnetic field. And then, once I get outside, it's proportional to 1 over R, with a nice point where it does match up. So if we look at our graph right here, this would be the magnetic field versus the radial distance. It's linear, and then it goes as 1 over R out here. And it is continuous. So this is proportional to R, this is proportional to 1 over R, which looks a whole lot like going inside and outside of a conductor in Gauss's law, except in Gauss's law, this was R squared, this was still linear. It looks like we're going inside and outside of a planet, where this was R and this was 1 over R squared. So it has a lot of things we've already seen before, which is really nice. Now, if you notice, at the position capital R, in other words, when I'm at the length of the wire, this R, this would be mu naught I over 2 pi big R. This would be mu naught I big R over 2 pi big R squared, which cancels the R's, and they turn out to be the exact same thing. So it is continuous at this point. So again, notice the similarity of what's happening for Gauss's law, and most students who did well with Gauss's law do very well with Ampere's law because they already know many of the major concepts. That you only include the current that's inside, just like you only include the charge that was inside with Gauss's law. Now, one thing that can be thrown at you, although it's a little bit more rare than it is with Gauss's law, is what happens if the current density is changing? What happens if you have a current density that changes as you go through? And for that, I'm going to introduce you to the idea of current density. That current density J is current per area. So that means we're getting a certain amount of current that we're looking at per area. Because if you look at the wire, you're seeing this as a face, and the face of this is the area. We're not worried about the rest of it that's happening through the volume because this is moving through here. These are charges that are moving. So when we have the current per area, if we really want to find out what the whole thing is, if it were just constant, it would be easy because the current would be the current density times the area. That's like the last example. In the last example, it would just be the current would just be the current density, a constant, times the area. But what if it's not constant? If it's not constant, then what's really happening is something like this. The current is the integral of J dA. Now let's take, for example, a wire just like this, where that's a normal cylindrical shape. If we want to find out what the area is of this, then what we would do is we would cut a ring out of it, really like a cylindrical ring of radius little r, and you cut that out with your mental scissors. You take it out, you cut it out with your mental scissors, and then you cut it right here and unfold it. And if you unfold it, you'll unfold it into something like this. There'll be a strip that has a length 2 pi r and a thickness dr. So that means the area will be, a little piece of area, will be 2 pi r dr. And that's what will go in here for the cylindrical wire. So if you're given something like this, and I actually do one of these, or give you a problem like this on one of the worksheets, that I'll ask you to find out what the magnetic field is for a current density where the current density is C times R, what you're going to have to do is something like this to find out the other side. Because on the integral of B dot ds equals mu naught I, you'll have to do this for I. So essentially you're going to have an integral on both sides. One is the integral of B dot ds, but that's just B 2 pi r. This you'll have to do this whole business here where dA is right here. So, but we've done things like this before. We just did it with different shapes and other things in Gauss's law. So we've been doing this for a long time. We even did it a long time ago with moment of inertia. So this is not something new that you're actually addressing with Ampere's law in total concept. It's just a different application of the same kind of concepts, but this time we're trying to find magnetic fields. So the last thing we want to talk about today with Ampere's law is something called a solenoid. Now hopefully you've watched the video on how to make an electromagnet, and it's pretty easy. All you need to do is wrap some coils of wire around a core, and then once you do it, attach it to a voltage source, and you have yourself an electromagnet. And I'm going to draw one right here. This is a solenoid again. So in this case, if you take a core like this, and the way I usually draw it is you make some integral symbols, sort of, not exactly integral symbols, sort of, but there we go. So I'm wrapping coils of wire around this. And my father actually taught me how to do this a long time ago, like when I was a kid. All he did, he took some wire, wrapped it around a nail, and then attached it to a battery, and all of a sudden you had a pretty strong magnet, especially because the domains inside the nail became lined up. So this is an electromagnet, and a very easy one to make again. Now, what we're going to do is we're going to examine this as if we cut it in half. As if we cut it kind of right down this section right here. And what we saw when we did that, if we're going to do that, is we would see that certain currents are going to come out at us and certain currents are going to go away from us. So I'm going to have this current, this current, this current, this current, this current, and this current coming out at us. These are coming away from us. And I'll show you how this pattern works here in a minute. So the idea here is that because I cut it in half, this is coming out like this, coming out like this, coming out like this. So this current is coming out here, then it's coming out here, then it's coming out here because we cut it in half. Now the effect of this is that the magnetic field inside a solenoid is very straight. And we're going to assume this solenoid is infinite in length because that way the end effects go away. There's a little bit of bending that happens at the end, but we're not going to worry about that. We can use our right-hand rule again to find it out, but I'm going to show you another right-hand rule that might make it easier. So what we can do, I can take my thumb here, point it in the direction of the current, curl my fingers in. The way it goes in, it just kind of comes in and hits going this direction. It's coming down into here and it's hitting this direction. I have my thumb here, curl in. Notice it's going the same direction. And each one of these wires will curl around so that they're all having a tangent right here through the middle that points, in this case, to the right. So I would make this one go around like this. At this direction, it's going this way. I'd make this one right here go around like this. This direction is going this way. And then this one builds on top of that, so now it's going that way. And this one builds on top of that, it's going this way. And therefore, the overall magnetic field in a solenoid, because it builds off all of these pieces, is nice and straight for one thing, and in this case, to the right. Now, in this unit, we only need two right-hand rules. We only need our forces rule, which is thumb up for current, fingers in the direction of the magnetic field, and palm is your force, that's it. And then curl your fingers in the direction of the magnetic field after your thumb points to the current. Those are the only two we need. But I will show you one more that might be helpful. If you have a solenoid, an electromagnet, and you want to find out which end of it is north, all you do is take your right hand and grab it in the direction that the current's going. Notice the current's going around like this. It's coming out like this. So I grab it in that direction. My thumb is the north pole of that magnet. So this would be north, and this would be south. In a sense, what we've made is we've made a bar magnet out of a bunch of wires when we do that. And again, these can be pretty strong. So how do we analyze this with Ampere's law? And because it's a little bit different, it doesn't look like some of the wires we've done. So how do you deal with that? Well, we go to Ampere's law. The integral of B dot ds equals mu naught I. And B dot ds seems a little strange because what I have to do, I have to map some kind of path that lines up with the magnetic field and then goes all the way around and surrounds some currents. So here's how I do it. I make a path in this direction, and when I do that, I've lined up with the magnetic field here, and then here I've enclosed some currents. In this case, I enclosed two currents. It doesn't really matter how many I enclose, but I've enclosed two currents right there. So let's see how this turns out in the mathematics right here. So the magnetic field inside a solenoid is really constant. So that's good. That's just B. And then the path that I went on. Well, the problem is not all of it counts. The only part that counts is the part that lines up with the magnetic field, because it's the integral of B dot ds. So this part right here, the length of this, doesn't matter. This doesn't matter because it's perpendicular to the magnetic field and it doesn't matter. It's not contributing anything in that case. This piece doesn't matter. It's not lining up with the magnetic field, that's it. This piece right here isn't even in the magnetic field, so that doesn't count either. The only part that matters is this piece right here. And what I'm going to do is I'm going to call that length L. So what's the integral of B dot ds? It's B, the magnetic field here, times L, because that's the amount that matches the path. So it's B times L. Mu naught. Well, how many currents are inside my path? Well, the number of currents that I have here is 2, but this is just a representation. I could have made this bigger, and then there'd be 3. Or I could have made it bigger, and then there'd be 4. What I'm going to do is I'm going to give it a generic value. I'm going to say that the number of currents in here is N currents. That's how many currents that I have in there. So we can now solve, and it's pretty easy. The magnetic field is mu naught Ni over L. And this is correct. This is totally correct. But no one writes it like this. The way they write it is this. B is mu naught little n times I, where little n is the number of loops per length. So how do you make a strong electromagnet? First thing you do is you wrap the coils really tight. So the number of loops per length, the more coils we have really, really close together, the stronger your electromagnet is going to be. Next, use a lot of current. As a matter of fact, when you see with the thing that my father did where he just wrapped it around a nail and attached it straight to a battery, the only resistance in the wire was the resistance of the wire itself. So it really didn't have a lot of resistance, so the resistance was low, so the current was really high, so it was a powerful electromagnet. It did burn out the battery pretty fast though. But there's one other thing that in that first part that my father put together that you can do. He wrapped his around a nail. Now you don't have to. Like you just wrap this, you'll get an electromagnet by itself. But if you wrap it around a nail, what happens is the domains inside the nail line up and make this a much stronger electromagnet. They do. And technically at that point, it will no longer be mu naught. because mu naught is the permeability of free space, it will be the permeability of iron. It'll be mu Ni. And this is a lot stronger than this. It's a much bigger number. I don't happen to remember what the number is, but because the domains will have lined up, you will have produced a much stronger electromagnet. And again, how do you make it? Have a core of some kind of magnetic material. Iron is great. Wrap the coils really, really tight. You could even do multiple wrappings on top of them. Just make sure they all face the same direction. And then put a lot of current in there and you'll be all set. So what we talked about today was Ampere's law, the second part, how to analyze a few different situations. I've got some different problems for you on there. You're going to be working on problems 8 through 11 on the Ampere's law worksheet. That's number 3 of our worksheets. We only have one more concept left. That's the Biot-Savart law. And then you'll be time to review and ready to do the progress check as your test at the end. So happy Monday, everybody. Hope you guys are doing great. And again, watch out for an email from me that's coming soon that is going to detail what's coming up with the AP test. And you probably already received that email from the College Board. All right. Have a good day, everybody. Hope you guys are staying safe.